All right, continuing with chapter 16. In this section, we're gonna be learning about what we call ideal gas law. So that means looking at a microscopic description of an ideal gas. Okay. So one of the things, if you remember, is we have talked about pressure in chapter 15. We know what the pressure is and how the pressure basically in a container can be due to the fact that molecules or atoms collide with each other and with the container wall. And we know then there is a temperature of a gas, right? Then in terms of like, let's say temperature, exactly what it is, we talked about in the first part of this chapter, kind of like a hotness and coldness and things like that. But eventually we're going to see that temperature actually have a much more important significance, like let's say, physical significance. But in any case, so let's think about like this. So let's say you have a system where your system here is some kind of container with a gas in it, right? Because it's mostly for the gas. Let's say container with the gas. So let's say here's some kind of container with the gas molecules inside, and then we have several important things, right? Like a volume of the container, and then the pressure of the container right now, the temperature of the container, also, number of molecules inside the container. So those are, for the variables, right? Those are the variables that describe my state. Okay. Then we're going to try to then set up an equation that relates all of those, let's say velocity to pressure, to temperature, or how the pressure and temperature related, right? So how the pressure and number of molecules related and things like that. So those are the things we're gonna do. We're gonna do relate those and set up an equation which we call the equation of the state. And you can see, right, these are generally quite complicated because there are a lot of factors. These are some of the main factors, but there are a lot of factors going into play. If the gas is maintained at a low pressure, the equation of state becomes much easier. And this type of low density gas is commonly referred to as an ideal gas. Okay, so we are talking about an ideal gas, which is again, we can assume it's a low pressure and a low density gas. Um, Again, so this ideal gas model, right, requires us to do some assumptions, some simplifications. So we can assume that you have a system where you have some n number of molecules, or let's say atoms, and they move randomly. And I mentioned that molecules and atoms are always moving, so they are always in constant motion, and generally they're always move randomly. In some cases, you can force them to move in specific direction, but on their own, they always move randomly, and they exert no long range forces on one another. Okay, so there's basically when they, let's say collide with each other, those um, those forces are just due to the fact that they physically hit each other. That means they don't exert any type of other electric force or gravitational force. Some of those long range forces on one another are so small that they occupy a negligible fraction of the volume of the container. It's also important because if you have let's say, a container with V representing the volume of the container. And if you have molecules that are small, then their size can be ignored when I'm representing this volume. Okay. But imagine if those are molecules that have significant size, then you can see, right, available space now in my container becomes a whole lot less because I have to factor out, I have to subtract all their size, all the, let's say all the space that those molecules occupy. I have to subtract and only have the space that are not occupied by molecules as part of my volume. Ideally, that's what you would need to do if you're doing the actual experiments and things like that, because molecules still, let's say, as small as they are, they have a size. And if you have a large number of them, so some parts of the or some space in your container no longer available to you because they are occupied by the molecules. Here we're saying that that's not the case. We can assume that they are so small that they, let's say they may be occupied like, let's say, 0.002% of your volume and things like that, or something like that, and you can completely ignore them. All right, so amount of gas in a given volume is conveniently expressed in terms of the number of moles. All right, so what does it mean? It means that, if I take the molecules inside my container and I, let's say, separate some of them, and then I, let's say separate a group here. And this group is exactly 6.022 times 10 to the 23 molecules. Okay, that means in that group, right, I have exactly this number of molecules or atoms. Then I'm going to call this Avogadro number of molecules, N sub A. And remember, N is the number of molecules, N sub A is Avogadro number of molecules. That means this is exactly this many molecules. Now, this many molecules we also define to be 1 mole. Okay, so 1 mole of a substance is that amount of substance that contains Avogadro number of molecules. That means I can say that this many molecules, which is again Avogadro number of molecules, I can just represent it with 1 mole. Just easier, right? That means if I have 4 such, let's say, groups, then my container has 4 mole, in terms of the, in a way, like a number of molecules, right? So it's easier to just say 4 moles rather than, like, let's say technically 4 moles means, 4 times this Avogadro number, right? Which is roughly, what is it, like 24 times 10 to 23, right? It's just easier to represent everything in terms of moles. So just like, let's say, the distance, right? So when distance becomes much greater, you can have a different, unit representing that. So millimeters becomes too big, use meters. Meters become too big, use kilometers. Kilometers become too big, I don't know, astronomical units or light years and things like that. So those are the, ways we can make something that's really large, more compact. So that's why mole now is going to be used to represent number of molecules. So you can say this n, which is number of moles, can be determined 2 different ways. One can be, you can use this, what I just showed you, that number of moles is total number of molecules divided by Avogadro number. Because remember, so in a way, what we have, the total number of molecules is equals to, n times Avogadro number. Remember, I had 4 groups of Avogadro number, right? So that's kind of what I have. So total number of molecules is number of moles times Avogadro number, and number of moles is a ratio of the total number of molecules over the Avogadro number, which in this case I will get again 4. Then you can also calculate from the total mass of your substance. That means the total mass you have of the molecules in your container. Generally can be given, let's say, kilogram or gram. So let's take this in terms of grams. Then you have divided that by molar mass. So the molar mass of a substance is usually given as gram per mole. That means how much is, or like in terms of grams, right, is 1 mole of that substance. So then you basically gram per mole. So you can see, right, the grams cancel out. So then you have units in terms of the mole. Okay. So again, m is the mass of the sample, the total mass of the sample, and then big M, right, is the molar mass, which is the mass of 1 mole of that substance. So there are a couple of equations for the number of moles. All right. So then one thing we can do here is I have a simulation that we can use in order to understand how these things are related to one another. And it's a nice way. You can find it on Canvas page. It's a nice way of seeing that visually how those things are related to one another. So for example, here's a system where we have a V representing its volume. Here's a pressure gauge that gives us the pressure. Here's a thermometer that gives us temperature in Kelvin. And this is a way of pumping molecules in it. Okay. Also, this is a source of basically adding, let's say, think like it's increasing temperature or decreasing temperature. Let's put it that way. Now, our goal is this. Let's say pressure is defined in terms of if you have molecules in your system, let's say in that volume that you have, right? And the pressure here is due to the fact that they're colliding with the wall of that container. And obviously, if there are no molecules, there is no pressure, because no molecules means then your pressure is zero because there is no collision. So that means, for example, now if I pump more molecules, what will happen to the pressure? We want to look at it in terms of, so if I pump more molecules, so here we're pumping more molecules, well, you can see then pressure increases because now those molecules start colliding with the wall. That means now this is the amount of, I have some n number of molecules right now, and my pressure, let's say roughly 32 atm. What happens if I add the number of molecules? So I pump more, well, pressure increases. That means, pressure increases if I add number of molecules. What if I remove some molecules? Then I can see pressure decreases. So I have less number of molecules in my container, lower pressure. That means I can say that pressure is then directly proportional to the number of molecules. Okay. All right. So another thing we can, explore here is how the pressure related to the volume. So right now I have the volume, um, and I have a way of changing the volume using this knob over here. So think like if I decrease the volume, pressure increased. Decrease even more, it increased even more. Now if I increase the pressure, the volume, pressure decreases. Make the volume even bigger, pressure decreases. Even bigger, pressure decreases. That means what I have here is I have increase in volume decreases pressure, or decrease in volume increases pressure, which means pressure is inversely proportional to the volume. So the pressure is in proportion to the inverse of the volume. Okay. All right. So the next we can explore in terms of what happens if I change the temperature. For example, right now I have roughly 38 atm, and I'm going to add heat, which basically increases the temperature. So you can see the thermometer gives me now higher, temperature, and I can see then the pressure increases. Higher the temperature, higher the pressure. Or I can lower the temperature by putting on some kind of cold bath, right? And then the pressure decreases. That means it's directly proportional to the temperature. So pressure is directly proportional to the temperature. Remember, it's in Kelvin. Okay. That means if I increase the temperature, I'm increasing pressure. I decrease the temperature, I'm decreasing the pressure. Okay. So that means those things like pressure, volume, temperature, and number of molecules related to one another, and those are variables of my state. So they are related using those which were experimentally right now determined. Okay, now that means I can write it in terms of pressure is proportional to number of molecules, temperature, and inversely proportional to volume. So in a way, this is my you know result from this type of experiment. All right, so let's go back here, then let's see what we have. Each one is actually very specific, important, significant. There's also a law on that. For example, when a gas is kept at constant temperature, that means we didn't change the temperature, but we only changed the volume. Its pressure is inversely proportional to its volume. That's basically when we just change the volume. This is known as the Boyle's law. So Boyle's law, that means we didn't change the number of molecules. That was constant. The temperature was constant. We just changed the volume, and then we could see that pressure is inversely proportional to volume. Now, next, remember we did not change the a volume, but we just changed the temperature. So if when the gas is kept at at constant, well, this is constant pressure, the volume is directly proportional to temperature. This is Charles' law. This is basically says when a gas is kept at constant pressure, the volume is directly proportional to the temperature. Let's explore this, because this also allows me to says hold constant. So I can hold the pressure constant. Okay, so pressure is constant, and sorry, this is pressure constant. And the idea was that when the pressure is constant, if I change the temperature, then it, instead of like affecting pressure, which cannot be changed now, is going to affect the volume. So let's do that. Well, I'm actually not able to do that right now for this particular simulation. Okay. All right. So I guess I can do it in terms of this. I'm changing the volume and I can see how the temperature changed. That means I can't vary the temperature, but I can vary the volume and see the effect. So remember the volume and you know uh, a temperature. So we were told that when a gas is kept at constant pressure, the volume is directly proportional to the temperature. So let's see, 192 Kelvin, and this is my volume. That means if I increase volume, temperature should increase, and it did increase. Again, if I increase more, the temperature will increase. It did. Temperature increases. But if I decrease the volume, temperature should decrease, and we see that as well. So every time I decrease the volume, the temperature decreases. I increase the volume, temperature increases. All right, so then the last one says when the volume of the gas is kept constant, the pressure is directly proportional to the temperature. That we also saw. That is Guy-Lussac's law. All right, so we have Boyle's law, Charles' law, and Guy-Lussac's law representing, how those variables related to one another. All right, that means our experiment gave us that pressure is proportional to number of molecules, and then it's proportional to, let's say, temperature, and inversely proportional to the volume. Okay, that means from here I can set up an equation where if I go from proportionality sign to equal sign, then I can introduce a constant. Okay, so but before that I can also represent it in terms of this. Remember, so pressure is proportional to, remember, number of molecules is number of moles times the Avogadro number. So I can technically say that this is number of moles times Avogadro number times temperature over volume. I can write it like this. Most of the time, what we do, we move the volume to the other side. So we say, P times V is proportional to NT, or P times V is proportional to the Avogadro number times number of moles times temperature. So those are the proportionality signs we have in terms of this. Every time we go now from proportionality sign to equal sign, we have to introduce a constant. So then we can do that by rewriting this in terms of PV is equals to, in this first equation, this becomes KB, which is a Boltzmann constant, times N times T. In the second equation, PV is equals to, then becomes a gas constant, which is, well, let me first put that, the Boltzmann constant, right? KB times number of moles times Avogadro number times T. Okay, those are my equations now. Okay, now one thing we're going to see that I can have a constant R that is equals to the ratio, or in this particular case, let me write like this: KB is actually equals to the gas constant over then Avogadro, number. So if I come back here, replace this with R over NA, then NA can cancel out. So when I have N, R, and T. That means those are my two different equations, which again we're going to see. So here's the first one again. The second one actually, PV equals nRT. So remember here, what we're saying is that this was initially written as KB times number of moles times NA times T, but then KB is equals to the gas constant over the Avogadro number, so it kind of cancels out. So we then have this format over here. So this is known as the ideal gas law equation. R is a constant. You have two values for that, 8.314 joules per mole Kelvin, and another one is 0.08214, which is liters ATM mole Kelvin. You can see, right? The difference here is that on the left side of this equation, if the pressure here is newtons per square meters, then times volume, which is cubic meters, if I cancel those, I end up with the newtons times meters, which is nothing but joules. Okay, which is nothing but joules, which means that's where this joules coming from. That means on the left side, my units are joules. So on the right side, I need to also have joules. And if I'm using then the joules, let's say, then I have to use this equation, this version of that, which is 81314, which means on the left side, pressure and volume has to be in pascals, which is equivalent to Newton per square meter, right? And cubic meters. That means it's in SI units. Pressure and volume is our SI units. But I can also have a pressure in ATM, like we already know, right? And volume in liters. And I can technically use them as well. But in that case, I have to have the the gas constant in terms of liters times ATM mole per Kelvin. Temperature, remember, it's not a delta T, but T, so it always has to be in Kelvin. All right, so from this, you can determine that 1 mole of any gas at atmospheric pressure and at 0 degrees Celsius is 22.4 liters. Okay, so you can determine that from this particular constant. All right, so again, this is then the second equation that I showed you, which is PV equals N times KB times T. Okay, and again, this is an important equation because we will be using this later on as well when we derive the physical, significant equation for the temperature. So this equation actually going to be used later on. So KB is a Boltzmann constant. It's not the same as a spring constant or anything like that. So it's a different K. That's why you always make sure that put the KB, right, the B as a constant, the subscript, so we know that it's a Boltzmann constant. It's 1.38 times 10 to the negative 23 joules per Kelvin. All right, so then what you have to do is just look at which equation is more important. Like, let's say not important, but in terms of like which one is more useful for that particular problem, right? Are you given in terms of number of moles or are you given in terms of number of molecules? So then you can either use second version of the ideal gas law or the first version. But one of the things we do here is we can then use these equations to describe, let's say, one state. So let's say here's my molecule, here's my volume with molecules in it. And what I can say here is this. Okay, so I have, n number of molecules or n number of moles, right? Kind of like, and volume of the container, and then the pressure and the temperature. So then using these equations, right? So the equation 2 for the ideal gas law, or equation 1, which is an RT, if I give you some of the unknowns, and then let's say in this particular state, I'm missing one variable, you can use then either equation 1 or 2 to find that particular unknown variable. I can also do when I change my state. So let's say I can say this is my initial state. So this is my initial state like this, where my initial state has number of molecules 1, volume 1, pressure 1, temperature 1, like that. And then I can change something. So here's my state 2. In my state 2, I might have some of the things are different. So then I have N2, or number of moles 2. I might have a different volume, different pressure, and different temperature. And then one of the things I can say here is this. So using the equation from the first state, which will be in terms of P1 V1 equals N1 R times T1. So this is the state 1. And then here I can have state 2, where I have P2 V2 equals N2 R then times T2. I can even relate them because of the gas constant. See, R is equals to V1, P1 V1 divided by N1 times T1. Cannot have no room, that's why. So R equals P1 V1 N1 over T1. In equation 2, then R is equals to P2 V2 over N2 T2. Well, that means those two are also equal to one another. That means I can write it like this. I can say P1 V1 over N1 T1 is equals to the ratio of P2 V2 over N2 times T2. Okay. That means using this ratio for state 1 and that ratio for state 2, I can cancel things, I can factor out, and then eventually find some of the unknown. All right, so that's what we're going to do. So let's say we have several examples that shows you how you can use these equations to not only find some unknown in this in just one single state example, or you can also have 2-state examples or even 3-state examples, right, where you can have those ratios, right, allow you to then calculate some of those things. All right, so let's look at an example here. So you have a 2-liter tank contains 4.86 times 10 to the negative 4 kilogram of helium at 18 degrees Celsius. The molar mass of helium is 4 gram per mole. How many moles of helium are in the tank? What is the pressure in the tank in pascals and in atmosphere? All right, so in this example, we're just basically given one system where we're given the values for, let's say 20 liters is just the volume, right? Then the mass, 4.86 times 10 to the negative 4 kilogram, that is the mass of the substance, right? And then the temperature, we're given 18 degrees Celsius. But remember, this is, um, should be in terms of the Kelvin. So we have to say that's all right. So the temperature is 18 degrees plus 273. So this is then 291 Kelvin. Always we have to convert to Kelvin. All right, so we're also given the molar mass, which is 4 gram per mole. So which I can write it in terms of 4 times 10 to the negative 3 kilogram per mole. They're equivalent. All right, so then for part A, it says how many moles of helium are in the tank. All right, so remember, there are two equations for the number of moles, right? Total number of molecules over Avogadro number. Avogadro number I always know, but in this case, I don't know what the total number of molecules is. So I go to the second equation, total mass over the molar mass. Now that one I have. So it's 4.86 times 10 to the negative 4 kilogram over 4 times 10 to the negative 3 kilogram per mole. And I can use this to calculate then 0.122 mole. Okay, so this is the number of moles. Okay, generally when you're writing as a unit, it's MOL, just mole. All right, so part B then, think like this. Now for this single state problem, right, I have N number of moles, which is 0.122 mole. I have volume, which is 20 liters, which then I can convert into, cubic meters by saying times where 1 liter is 10 to the negative 3 cubic meters. So it becomes 20 times 10 to the negative 3 cubic meters. Okay. Then I also have temperature, right, which is 291 Kelvin. That means number of moles, volume, and temperature. And then part B says, what is the pressure in pascals and in atmospheres? So then one thing I can do here, I can say, all right, so then pressure is equals to, using this equation, right? PV equals, then I use a first equation or second equation of the one equation that has number of moles, which is nRT, then use this to solve for the pressure. nRT divided by then V. So 0.122 mole, then the constant, gas constant, because everything, I'm going to do in terms of pascals, right? I'm using 8.3145 joules per mole Kelvin, then times 291 Kelvin, then divided by 20 times 10 to the negative 3 cubic meters. Okay. Now the idea is that joules is then newtons times meters. So then at the end, I'm going to get my correct units. All right. So if I calculate pressure, I'm going to get 1.47 times 10 to the 4 Pascal. Okay. So which is basically the pressure in Pascal. Now, in order for me to get the atmosphere, I can do two things. I can take this and I can multiply where then 1.013 times 10 to the 5 Pascal is 1 atm and calculate this, pressure in atm. Or I can, use the equation where nRT over V, everything is in then, all I have to do is just have the volume, right, is in liters. So that this can be just 20 liters. And then this is 0.122, but I use the second, gas constant, 0.08214. Remember, this is liters atm per mole Kelvin, then 291 Kelvin, right? Then I can use this to calculate, pressure in atm directly. So two things, right? We can do the find in Pascal, then use this conversion factor to go to from Pascal to ATM, or use the pressure equation where volume in liters and gas constant in liters ATM to calculate that as well. All right. Here's another example. Gas is contained in an 80-liter vessel at the temperature of 20 degrees Celsius. This 8 should be actually degrees. And the pressure of 9 atm. Determine the number of moles of gas in the vessel. How many molecules are in the vessel? All right. So we're given the volume, which is 8 liters, and we're given the temperature, which is 20 degrees Celsius. So I need to convert this into Kelvin. So plus 273 gives me 293. And this one can be converted into 8 times 10 to the negative 3 cubic meters. Like that. And pressure then is 9 atm. So if I need to, right, I can, convert this also into, let's say, a Pascal, 1.011 atm is 1.013 times 10 to the 5 Pascal. I can, convert it like this as well. All right, so I want to find the number of moles that I have. Okay, so for this one, again, they are technically have this equation, number of molecules per Avogadro number, which I cannot use. And then there's another one, number of moles is equals to mass, total mass over the molar mass. I can't use this as well. So, but there's one more equation where I can have, number of moles, and that's the ideal gas law, PV equals nRT. So then N is equals to PV over RT. So I can also get this equation. All right, so N is equals to, and again, in a way, I can, let's say keep everything in liters and ATM, or I can convert everything, right? So into Pascal and cubic meters, but use the appropriate gas, gas equation, gas constant, equation, or the value. But let's say here, pressure here is a 9 atm, where I converted is 1 atm is 1.013 times 10 to the 5 Pascal. And then R here is 8.314 N times mole Kelvin. So then 293 Kelvin for my temperature. This will be per Kelvin. And then from here I can per mole Kelvin. Let me do it like this, right? So it's joules per mole Kelvin. All right, so if I calculate this, I'm going to get 2.99 mole. Okay, so plug in everything and calculate to get 2.99 mole. Part B then says how many molecules are in the vessel. Well, molecules, then I can use this equation here, where then N, number of molecules, equals to moles times Avogadro number. So I have 2.99 multiple of the Avogadro number, right? Which is 6.02 times 10 to the 23 molecules per mole. Okay, then N is equals to 1.8 times 10 to the 24 molecules. Okay, so they have 1.8 times 10 to the 24 molecules, which is basically equivalent to 2.99 mole. Okay. All right, so this is basically this, again, how to find the number of moles and then use that to find the number of molecules. All right, so here's another example. So in this example, we have an automobile tire is inflated with the air originally at 10 degrees Celsius and normal atmospheric pressure. During the process, the air is compressed to 28% of its original volume, and the temperature is increased to 40 degrees Celsius. What is the tire pressure? That means basically what we do, we go from one state to another, right? So we'll find then the tire pressure and all of those things. So let's start from in terms of defining our parameters for the first state. So for the first state, we're given the temperature 1 is 10 degrees Celsius, which is 293 Kelvin. We're given that normal atmospheric pressure, which means then a pressure 1 is 1 atm, or 1.013 times 10 to the 5 Pascal. Okay. And then we take that, let's say V1 to be the volume of that first state. So we have, and then let's say I can also put like N1 is the number of molecules. Okay. Let me just let me remove this comma sign. So those are my initial, state variables. Then we go from here to the second state, where then temperature 2 is 40 degrees Celsius, okay, which is 273 plus 40. So this one is going to be what is it? Sorry. $313 Kelvin, and pressure is 28% of its original. That means I can say then V2 is equals to 0.28 of V1. Okay. And there is nothing about, let's say, number of moles being changed. So I can say N2 is technically then equals to N1. Okay. But, in terms of here, and then the question is, what is P2 once I change it? All right. That means, I'm shrinking the volume, I'm increasing the temperature. I want to know then what is the pressure. That means what I can say here is this. Remember that equation, right? So technically then I can say then P1 V1 over N1 T1, that ratio, right? Because I go from one state to another, R is a constant for both of them, so I can relate R to both states. Then P2 V2 over N2 times T2. The only thing here is number of moles, same before and after, so I can cancel them. So then what I end up with here is P1 V1 over T1 equals P2 V2 over T2. V2, then I can come back and say it's 0.28 V1, which will then allow me to cancel that V1 as well. And then we'll just rearrange and solve for, a P2. So then P2 is equals to T2 over T1 times there is 0.28 factor, right? Then P1. Okay. So T2 was 313 Kelvin. Then 0.28, then 293 Kelvin. All right. Then P1, which is basically 101 Pascal. Okay. That means now if I calculate, I'm going to get 4 times 10 to the 5 Pascal. That means my pressure increased from, 100,000 to 400,000 Pascal. So roughly a 4 times increase in my pressure. So that's part A. Part B says, after the car is driven at high speed, the tire's air temperature risen to, whatever I had, right, earlier. So it risen to 85 degrees Celsius. And the tire's interior volume increases by 2%. What is the new tire pressure? Absolute tire pressure. Okay. And the pressure in the ideal gas law equation is the absolute. So, all right. So to do that, then I calculate from in terms of given information, right? So that means, comparing to, let's call it state 3 to state 2. So what we had here is temperature right now for T3 is 85 degrees Celsius, which is 85 plus 273. I can calculate to be 358 Kelvin. then right now the volume increased by 2%. Okay, which means, the volume 3 is equals to 2% increase, which is basically written as 1.02 of the volume 2. Okay, of the volume 2, which is volume 2 already was 0.28 of volume 1. So in a way, that's kind of what I have. All right. So then again, going from here, I can look at in terms of what I'm given, right? So let's say ideal gas law comparing uh, state 3 to state 1. So remember, then in my state 1, I had temperature 1, which is 10 degrees. So that's actually, all right, I made a mistake over there, 283 Kelvin. So 283 Kelvin. So then pressure 1 was uh, basically 1.013 times 10 to the 5 Pascal. And then let's say V1 is the volume 1. So then I can again use the same thing, right? Assuming that N3 is still equals to N1. So I can say then P1 V1 over T1 is equals to then P3 V3 over T3. Okay. And then I can replace V3 with 1.02 times 0.28 V1. Okay. And then pretty much from here do the calculations. That means, I have P1, I have T1, I have T3, I have V3 technically, and N1, and just rearrange and just solve for P3. So P3, rearranging and calculating, because I could also cancel V1s, right? Rearranging and calculating. So I get 4.49 times 10 to the 5 Pascal. That means again slightly increasing pressure after this as well. All right, so that's how you can relate all of those, quantities. So you can, because again, there are some constant always, right? Number of moles don't change and things like that. You can always do that, right? P1 V1 over T1 equals P2 V2 over T2, or also equals to P3 V3 over T3. So those are all can be used to calculate some unknown quantities. All right, so the last section in this chapter talks about kinetic theory of gases. So in this case, we're going to consider this kinetic theory of gases, which is generally really complicated and very statistical. So we're going to make some, simplification and assumptions here. So this one basically represents description of the physical components of a system. So the number of molecules in the gas is large, and the average separation between them is large compared with their dimensions. Okay, that means there's one thing that we're going to have to consider this. So this is looking at, instead of macroscopic, which was the previous, let's say section, to a microscopic. See this microscopic description, which is what happens to the molecules and things like that individually. So we have to check this, right? And then for number 2, it says the description of where the components are located relative to one another and how they interact. So basically represent that the molecules are distributed uniformly throughout the container. Any molecule can move in any direction with any speed. So they can move randomly with any speed. The molecules make elastic collisions with the walls. Okay, elastic means that energy is conserved and the momentum is conserved. That's the important thing about elastic. All right. So the description of the time evolution of a system. So this theory also represents that. It describes the description of the time evolution of the system. The system has reached a steady state situation, microscopic description of the gas, and these are the microscopic. Microscopic variables are volume, temperature, pressure, and things like that. They remain fixed. Now, it also represents a description of the agreement between predictions of the model and actual observations, and possibly predictions of the new effect that have not been observed. So this model makes specific prediction relating macroscopic measurements to the microscopic behavior, predict how pressure and temperature are related to microscopic parameters. Again, the pressure and temperature and volume, those are microscopic, representing sort of like entire system, right? It's entire volume of the entire system, temperature of the entire system, where then we can have other things like, let's say, if you're looking at the individual molecule, how fast the individual molecules are moving, how much kinetic energy does it have, what type of force does it exert, and things like that. So those are the microscopic, so kind of like a molecule or a particle, specific. So to do that, we have basically a rather complicated theory, which is going to look at sort of like a surface of that. So you can see, right, it represents a system where you have a volume. So you have d by d by d, right? And you have a molecule moving that has a mass m naught and moving with some velocity. And obviously, one of the things we know here is I'm looking at just this molecule, but I know there are n number of molecules in the system. Okay, but again, we're going to focus on one molecule of mass m naught. Okay, and we're going to say that as this molecule is moving, it's going to move and hit the wall of the container with some force. So if I choose, like, let's say this area A, I know that it's going to hit with some force, and it's going to then have the same force acting on it from a wall. And one thing we know, that there's going to be a change in momentum. So there's going to be change in momentum, where momentum mv final minus mv initial of the molecule technically end up giving me 2 times mv, because one is in opposite direction. And then remember, the change in momentum was also equal to the net force times delta t. So that means you have introduction to the force, introduction to the mass, and everything together. But again, I'm not going to go too much into this derivation of this, let's say, kinetic theory of gas. The idea here is this: when we plug everything together, so this force then represents, can be related to the, pressure times area. Remember, force is pressure times area, which is then pressure introduces in this equation, where pressure is the microscopic quantity. This V, which I have V final, V initial, those are then the microscopic quantities, right? Those are specific for this molecule. But then I can relate, some of those things together and end up with one equation for the pressure eventually, right? The pressure equals then this, whatever I have on the right side, which is 2/3 n over v times 1/2 mass times average velocity square. Now, what is average velocity square? That's kind of like, so average velocity square is basically something like this. So this represents the velocities, average velocity, right? Remember, average velocity will be this, average of 1 plus, velocity 1 plus velocity of 2 plus velocity of 3, divided by n. That's my average velocity. Then I take this quantity and I square that. So that's what it is. And then what I have here is I have then 1/2 mass times average velocity square, which technically gives me average kinetic energy. Now, average kinetic energy, again, represents the kinetic energy of my molecule 1 plus kinetic energy of molecule 2 plus and divide by n number of molecules. So it's the average kinetic energy of my, of all the molecules in the system. Okay. So then the pressure is equals to 2/3 nv, then 1/2 m naught v naught squared. So this quantity is then the average kinetic energy. Okay. Then the pressure, which you see from this equation, right? Pressure is proportional to the number of molecules per unit volume. And this is number of molecules per unit volume, directly proportional to that. And then the proportional to average translational kinetic energy of the molecules, which is this. It's average translational. Remember, translational means that there is no rotation, just linear motion. And that's what we have. The pressure, which is microscopic quantity related to this. So this relates the microscopic quantity pressure to the microscopic quantity of the average value of the molecular translational kinetic energy. Okay. That means, we can write this as move the V to the other side. So it becomes PV, which is from the ideal gas law equation. So PV equals, and on the right side, we have just 2/3 number of molecules times 1/2 m naught V naught square. Okay. So again, this comes from the fact that this can be written as 2/3 n times K average, which is the, again, kinetic average kinetic energy. Now, the left side, which is PV, according to the ideal gas law that I showed you, also equals to that, right? Number of molecules times Kb times temperature. That means the left side, which is N Kb times T, equals to the right side, which is 2/3 N times average kinetic energy, which means canceling the N, which is number of molecules, and dividing both sides by the constant Kb, we end up with this equation, which is temperature. T is the temperature in Kelvin, then equals 2/3 times Boltzmann constant times average kinetic energy, which in a way, what we end up with, if you kind of rearrange, right, move this, 2/3 kb to the other side, so it ends up with this 1/2 mv average square equals 3/2 kbt. Look, kb is a constant, right, and things like that. So what I have here is this quantity here is the average kinetic energy, and it's proportional to this quantity here, which is the temperature, which means that it represents temperature as nothing but the average kinetic energy of the molecules inside your system. That means temperature is not some quantity that representing hotness or coldness. Physically speaking, the temperature represents average kinetic energy, how fast your molecules moving in the system. So if they move faster, the temperature increases. If they move slower, the temperature decreases. So that's why the temperature is basically is another representation of the energy in your system based on the kinetic energy of your system. So that's why how fast your molecules are moving basically gives you their kinetic energy, right? Because kinetic energy based on their speed. That's why when they stop moving, when basically at some point, right, when they stop moving, when the pressure is zero, there's no collisions and things like that, then the temperature is also zero, which is pretty much what we call absolute zero. Remember, absolute zero when the temperature is zero and there is no pressure. No pressure can only happen when the molecule is not moving and not colliding with the wall. So that's basically what this represents. Okay. So because we have, let's say, three dimensions, right? So that you can also look at this in terms of the y direction and the z direction. So this is known as in terms of the degree of freedom. That means you can write this relationship three different ways. In terms of, let's say, if the molecules were moving along the horizontal axis, you have this equation, or y along the y-axis, you have another equation set, and the z-axis. So then each translational degree of freedom contributes an equal amount of energy to the gas, which is 1/2 kb times t per molecule. So in general, the phrase degrees of freedom refers to the number of independent means by which the molecule can possess energy. So that means it can have 3 degrees of freedom from the translational energy. That means it can move X, Y, Z. There's also vibration and there's also rotation. So that means additional couple of ways of, couple of types of energy. All right, so that's why we're going to look at what we call theorem of equipartition of energy, which is each degree of freedom contributes to 1/2 kb times t to the energy of a system, where possible degrees of freedom are those associated with translational, rotational, and vibrational molecules. The total translational kinetic energy is just n times the kinetic energy of each molecule. Okay, so E total equals 1/2 mv naught. That's the kinetic energy, average kinetic energy. N is the number of molecules. So then it's equals to 3/2 n kb times t. All right. So since n times kb is equals to n times r, then we can just say that this is also equals to 3/2 nRT. That means this is the total energy. So the total energy equals to 3/2 nkbt or 3/2 nRT. Assuming that we never change number of molecules in the container, since it's, let's say, close to the environment, then total energy, so the total translational kinetic energy of a system is proportional to the absolute temperature of the system. That means the only thing is, proportional to is the temperature. That means the molecules moving faster or slower, which is amount of energy, right? They have that's why it will be based on that, can only affect the temperature. If they're moving twice as fast, then the temperature will be twice as fast. If they're moving, 10 times slower, then the temperature will decrease in a way, or in terms of kinetic energy, right? So it will be like, let's say, that similar. Obviously, because it's V squared, so there's a little of different proportionality, but the idea is that kinetic energy, right? This average kinetic energy depends directly on temperature of the system. All right, so for monatomic gases, so the translational kinetic energy is the only type of energy the particle of the gas can have. Therefore, the total energy is 3/2 nRT for monatomic gas. For them, diatomic, polyatomic molecules, additional form of energy are available, but the proportionality between E internal and T, remains. So another thing we do here is, because in our equation is V average square, so V average square, or this square root of V average square is also known as VRMS. Okay, so remember that equation was 1/2 mass times V average square, right, equals 3/2 KB times T. So if I rearrange, see this 1/2 cancel out. So then V average square is equals to, move around. So I have then 3 kBT over the mass. So now if I take the square root of both sides, see down the right side, I have 3 kBT over the mass, which is this guy over here. On the left side, I have one square root of, V average square. So I'm going to define that square root of V average square as this quantity that we call root of the mean square, so VRMS. That means this is equals to VRMS, or this is the second version of that. So that means a lot of times we can look at in terms of calculating this VRMS quantity rather than in terms of just the quantity that we call V. It's not the speed, but the RMS speed. So for a given temperature, light molecules move faster than than heavier molecules. It means you can compare their VRMS values. So VRMS of the hydrogen compared to helium and things like that. So for example, here we have calculating the RMS speed for the hydrogen at room temperature. It will be VRMS equals square root of 3RT over M using this version of the equation. So R is the gas constant, T is the absolute temperature, which is in Kelvin, M is the molar mass, which is 2 times 10 to the negative 3 kilogram per mole. That's for the hydrogen. And we get 1.9 times 10 to the 3 meter per second, roughly 2,000 meter per second. This is about 17% of the escape speed for the Earth. That means they're moving fast enough that all the hydrogen is basically gone from our atmosphere. Because this is an average speed, the large number of molecules having speeds much higher than the average can escape from Earth's atmosphere. Earth's atmosphere does not at present contain hydrogen because it has all bled off into space. They're moving so fast that means they can escape Earth's gravity. All right, so let's look at an example here. So you have 2 mole sample of oxygen gas is confined to a 5-liter vessel at the pressure of 8 atm. Find the average translational kinetic energy of the oxygen molecules under these conditions. All right, so we're given number of moles, which is 2 mole. We're given the volume, which is 5 liters, and we're given the pressure, which is 8 atm. So we want to find the average translational kinetic energy. All right, so using this equation, remember, so P is equals to 2/3 number of molecules per unit volume, then times mass times average speed square over 2. Okay. So remember, this quantity here is that, right? Average, kinetic energy. That means I can then rearrange this. So I can write this 2/3 N over V, then average kinetic energy, then rearrange where then average kinetic energy equals 3 P times V divided by 2N. And then just calculate this from here. So since we're given a number of moles, I can say then N here is equals to number of moles times the Avogadro number. And in a way, I can replace it there. I can say it's 3 PV, 2 times N times Avogadro number. Okay, so 3 times then the pressure. So the pressure is 8 atm. So then I can use this to calculate. Remember, kinetic energy has to be in joules. So I have to convert everything into joules. So that means this is 1 atm is 1.013 times 10 to the 5 Pascal. Then a volume, which is 5 liter converted to where 1 liter is 10 to the negative 3 cubic meters. Then divided by 2 times the number of moles, which is 2 mole, then times Avogadro number, 6.02 times 10 to the 23 molecules per mole. All right, so if I calculate the average kinetic energy, I'm going to get 5.05 times 10 to the negative 21 joules. So that's the average kinetic energy of the oxygen molecules under this condition.